Well, this is the Afon Morback, which flows through the heart of the Harlech Dome in North Wales. And I've come here because it's a good place to illustrate some geochemical prospecting methods that can be used to locate buried ore deposits. Now, if you wanted to find a mineral deposit, you could analyse the soil on a regular grid basis, but that's very time-consuming. And instead, we use a stream sediment sample like this, which contains fragments of all the various rock types up the stream. I'm going to try a simple field test for cold extractable copper in stream sediments. Now, it's important to take a similar sized mass every time, and this tiny scoop here contains about 0.2 of a gram. It's also important to have as fine a grained sediment as possible, because you can obviously get bias if you have large chunks with atypical copper contents in them. Now I'm adding a buffer solution which will ensure that we have the right pH for the copper-sensitive reaction. Add it up to the first mark, which is 10 mils. And now I'm going to add this green copper-sensitive reagent called dithazone. Now I'll put 10 mils of that in. The reagent turns red in the presence of excess copper, so we need to shake it up. And what we can do is add more and more dithazone until we get the green colour back, and then that will tell us how much copper there is in the sediment. And it looks as though in this case we've actually not got very much copper at all, because it's stayed green. In fact, the copper equivalent of this stream sediment is actually less than the 10 mils of dithazone that we added, and that's less than 30 parts per million in this particular stream sediment. So there are no anomalous values in this major drainage channel, but what we ought to do is to take a new sediment every time a tributary joins the main channel. Well, this looks more promising. I'm going to have to add some more dithazone to balance the copper in the sediment from this tributary. Well, I've had to add 40 mils of dithazone to get this neutral blue colour here, and that represents about 120 parts per million in the sediments from this tributary, compared with 30 parts per million or less from the main channel. So that's a contrast of 4 times for the 2 lots of stream sediments. And probably that means that there's a source of a copper anomaly somewhere up this tributary. Well, I've followed the tributary for about 400 metres upstream, and I've been finding fairly high values of copper all the way. And some of the highest values are actually in this peat bog here. Now, peat samples can be analysed in just the same way as stream sediment samples for cold extractable copper. And this is the last sample I analysed. It's got more than 125 parts per million of copper in it. These high concentrations led to a commercial evaluation of the area, and a thorough mapping exercise showed that this bog is the centre of the largest surface anomaly in the area. In fact, of all the soil and stream sediment samples, this is known to be the richest in copper. The 19th century miners worked this peat for copper. What they did was to strip off the peat and burn it in kilns, and they had a valuable residue of copper left in the ashes. But this isn't a primary mineral deposit. The copper was brought here both in stream water, though stream waters don't carry very much copper when they're at high EH, and also by secondary dispersion down the slope. And that means that the primary source of copper must lie somewhere up this slope. Well, the most striking feature of this outcrop is the yellow ochreous weathering. It's just like an oxidised iron-rich gossan overlying a sulphide ore deposit. But what about the fresh rock? It's not at all ochreous, but it's a dark greenish-grey metamorphosed siltstone. The other striking feature of this outcrop is the prominent sets of parallel joint planes like these. And it's along these joints and other hairline fractures that a disseminated form of copper iron sulfide, chalcopyrite, occurs. The chalcopyrite was brought here by hydrothermal fluids percolating through these rocks, probably from a diorite intrusion at depth. But today, of course, the rock face is exposed to weathering, and so copper is being removed. This leaves, though, the iron-3 hydroxides and oxides, which give the rather ochreous weathering. So copper's being removed down the slope by groundwaters and also by stream sediments in order to form the kinds of anomalies that we've been looking at in the peat and in the big stream at the bottom of the slope. Geochemical prospecting in this area, which is also discussed in the main text, together with geological mapping and data from boreholes, identified the region as containing a low-grade porphyry copper deposit. That's a type of hydrothermal ore deposit formed during igneous activity about 400 million years ago. So individual mineral deposits can be located by the geochemical mapping techniques of the type that we've shown you today. And in various areas of the world, mineral reconnaissance is being carried out to produce geochemical maps on this and on broader scales. Now, Professor John Webb, working back in the 1940s, pioneered the stream sediment method of geochemical mapping to find mineral deposits. And he also realized that variations in background might reflect the local geology.
Once that was apparent, then the next thing was to say, what else could it be used for, apart from finding mineral deposits? Because there are a number of problems affecting the community, such as agriculture and so on, where the distribution of the trace elements is a factor. So we spent some years making certain, as far as we could, that the stream sediment sampling followed by quick multi-element methods of analysis, producing atlases that people could use to look at the distribution of the trace elements for a variety of different purposes. Every time we upgraded the scale of the area, we came to a new research problem, handling the data, interpreting the data, and so in the end, with the help of grants from the Wolfson Foundation, we came to produce this atlas. Well, the atlas immediately showed some very obvious correlations with geology. Just for an example, the maps that everybody knows about the distribution of the granites in the southwest of England. And these are shown here by the map for nickel, where the granites naturally show up as blue, dark blue colors, which means very low values of nickel. And you will see the lizard here, where the nickel is obviously high, and that's related to the basic maps. Now, returning to the granites, the nickel shows where the granites are. But now look at lithium, and you will see now that only one of the granites, that's the St. Austell granite, a little bit of the Bodmin granite, and a small part of the Dartmoor granite, lithium is high. And those are associated with the distribution of chinic clay.
The atlas showed, as John Webb suspected, that there were good correlations between geology and trace element geochemistry. But that was rather an academic success. Work started in 1965 in Derbyshire to find a more practical application for the correlation. Dr. Ian Thornton from Imperial College worked on that project with Professor Webb.
In those days, we had a team of students who took samples from streams like this of the active stream sediment. That's the material that's brought down by the stream. They took samples at a rate of about 1 per square mile, 2.5 square kilometers, over an area of 800 square miles. In this area, we collected more than 600 samples from stream beds. We prepared and analyzed them back at Imperial College in London and plotted the results onto base maps. The large patch with no samples in the middle of the area is a limestone plateau with no streams at the surface. One of the most interesting elements here turned out to be molybdenum. Many samples in the area showed anomalous values of the element, ranging up to as much as 50 parts per million. This contrasts sharply with the average for rocks and soils of about 2 parts per million or less. The highest concentrations of molybdenum occur in the soils derived from the marine black shales of Carboniferous age, which surround the limestone. Though where the shales are covered by drift on the hilltops, the concentrations are much lower. Mr. Herridge has been farming here for over 15 years.
Shortly after arriving at the farm, we noticed that the young stock were performing badly. There was poor weight gain, had staring coats and diarrhea. We contacted the Ministry of Agriculture, who took blood tests which proved to be copper deficient. We injected these cattle with copper, and at present day they're perfect.
When symptoms are that obvious, there's not much the geochemist can tell the vet. And in fact, here in Derbyshire, the geochemical map for molybdenum confirmed the area in which clinical copper deficiency occurred in cattle. Now, the grass we see here and the hay that's formed from it normally contains an adequate amount of copper for the nutrition. It's not copper that's the problem, it's the amount of molybdenum that's present in the grass. Molybdenum forms an insoluble complex with copper in the animal and so prevents the absorption and the utilization of dietary copper. The geochemical map for this area showed that the extent of the molybdenum anomaly was far more widespread than the extent of the area of chemically sick cattle. So a series of experiments was started with the local vets and scientists from the Ministry of Agriculture. These showed that a large proportion of the local cattle had low blood copper levels. A further series of experiments giving copper supplementation to these animals gave rise to an increase in live weight gain, even when the animals showed no clinical symptoms of copper deficiency.
Well, that was the story which emerged in Derbyshire, but it had far wider implications. Later mapping efforts by the Imperial College team revealed similar anomalies developed on soils related to black shales in other parts of Britain. These anomalous areas probably represent between 1 and 2 million acres of agricultural land on which cattle could thrive more successfully if given copper supplements.
So we had a practical anomaly related to molybdenum in agriculture. But we also have anomalies which are not solely related to geology. And in this case, we'll take, for example, lead. Here you see the lead mineralized areas clearly marked. But amongst those, there are two, one at Avonmouth and one at Swansea, and these are related to smelting activity of quite recent years and have nothing to do with the geology whatsoever. But returning to the mineralized lead zinc areas, these too, indeed since Roman times, have been subject to the interference of man, which have enhanced and extended these anomalies by virtue of their mining activities and smelting activities.
Traditionally, these lead sulfide-rich veins have been mined from the surface to depths of over 100 meters, and the ores crushed and smelted on or near the site. These early operations have left acres of land contaminated by lead-rich waste and fumes or fallout from local smelting. This contamination affects large continuous tracts and also isolated patches in the surrounding fields. Although no mining is taking place at present, farming continues, and the health of the sheep grazing locally can be seriously affected.
When I came to this farm in 1958, I had no idea at all what the position was as far as lead poisoning. We had an idea that there was Belland on the farm, as the old people used to call it, but we just no idea of the extent of the lead poisoning that there was here. We soon realized that there was something drastically wrong when we lost a third of a lamb crop one year. It seems to affect the lambs up to about 8 to 10 weeks. The young lambs start to go stiff very often, unless they get in a place where there's a great deal of lead on the ground or they pick it up in one certain spot. Then you can find 3 or 4 lambs dead, all in a heap. I've lost a great many lambs, a great many stock, but we're getting to the position now where we can deal with it to some extent, but the trouble will never ever go away. It's always there to be, it'll be there for thousands of years.
The atlas only shows this area as a broad anomaly, but detailed soil sampling across these fields confirmed Peter Atkin's observations, and his continued good stockmanship enables him to overcome the problem of lead pollution. So now we have seen 2 examples of the effect of local geochemical anomalies on health patterns. To find out about some of the recent developments in geochemical surveying techniques, which should lead to a better understanding of these problems, I went to the Institute of Geological Sciences in London and talked to Dr. Jane Plant. Jane, so far in this programme we've looked at classical geochemical mapping and also at geochemical reconnaissance techniques. Now we followed this up with a couple of health problems in livestock related to local geochemistry. Now how will the IGS programme help with these problems?
Well, so far our input into studying trace elements and disease has been rather indirect because our main objective is to find new occurrences of metalliferous minerals. And for that we need very good point source data rather than the broad scale information that Imperial College have achieved.
I see, but IGS is using stream sediment samples, I believe, so how is your atlas going to be an improvement on the earlier ones?
Well, first of all, we've refined sampling and analytical methods, and we've also improved the data handling procedures, and we believe data presentation methods too.
I see. Well, let's take the first of those points. How have you actually gone about improving the sampling technique itself?
Well, we studied natural stream channels and looked at the chemistry and mineralogy of stream sediment samples. For example, the EH-pH regime is very important, and in peaty areas, for example, where water runs into the stream channel from the peat, iron and manganese oxidize when they enter the stream channel. They co-precipitate other trace elements, and this gives a falsely high reading of the bedrock geochemistry if one analyzes the stream sediment sample. Now we found that by carefully selecting our sample site and modifying the actual sampling procedure, we could largely overcome or at least minimize this problem.
So by studying the EH-pH regime, you were actually able to overcome a fairly serious problem that must have affected many of the earlier atlases. Well, that's a chemical problem. What about the associated physical constraints on sampling? What about sample size and the fraction you analyse? Are they important?
Well, we aim to collect about 100 grams of material using a sample density of about 1 or 1.5 square kilometres. The 100 grams isn't just any material, though. It's a very fine fraction, less than 150 microns, and again we determine both the sample density and the size fraction collected on the basis of orientation studies.
Okay, well, can you tell us something about the effect of sample size on the size of anomaly that you actually record?
Well, if we look at the case of copper, we can see the concentration of copper in relation to particle size, and I think it's fairly clear that if we collected a coarse fraction of sample, we wouldn't be able to distinguish mineralized areas from background areas, whereas if we collect a finer particle size, we get a much better resolution of mineralization and of different types of bedrock geology. As well as collecting this 100 mesh material, we had to develop a method to recover this quantitatively, and this means to use wet screening rather than the dry screening method.
Back in the IGS laboratory in London, field samples are prepared for analysis. It's very important to take a representative portion of the sample, as only 15 milligrams can be analysed from the 100 grams collected. Fine grinding ensures as homogeneous a sample as possible, and again helps to eradicate error from individual grains with unrepresentative element concentrations. The sample is compressed into a pellet and placed in an emission spectrometer, which analyzes a wide range of elements rapidly and cheaply, and that's essential in this project. An electric arc excites atoms in the sample, which emit light with a characteristic wavelength for each element. The intensity of each wavelength is proportional to the concentration of each element concerned. It's read on the spectrometer and stored in computer-readable form. Jane, you said the other improvement in your program is the way in which you handle and present the data. Can you tell us something about that?
Yes, well, we've adopted a very high level of automation, and most of the data are in these computer-readable files. This is a typical file from the Argyll Geochemical Atlas. It contains information for about 9,500 sample sites, and each of those sample sites has 30 element determinations.
That's an enormous amount of information. It looks pretty formidable. How do you actually translate that into a visual form?
Well, firstly, we prepare geochemical atlases, such as this one of Shetland. It contains geochemical maps for a number of elements, and if we look at this one of chromium, we can see some of the features of this map. Each sample site is shown by a line proportional in length to concentration, so quite simply, the longer the line, the more chromium. The information is overlaid on this geological base, and we can see here where we have gneisses and schists that the level of chromium is about 40 or 50 ppm. Over here it's about 500 ppm, and locally values reach up to 10,000 ppm. That's about 1% chromium.
So the presentation's quite different from John Webb's atlas, particularly in terms of scale.
Well, not only in terms of scale, but also in the amount of detail provided. If we look, for example, at this area in South Shetland, we can see that there are 2 sample points with high levels of chromium in an area where the levels are generally background. If we were to average or smooth all these data, we would simply have one value of above background information.
But because the original data are held on computer, I suppose there are lots of different ways in which they can be presented.
Yes, there are many possibilities. For example, the chromium map of Sutherland can be shown as a geochemical landscape or as a series of grid squares in which the trace element concentration is shown as a series of different colours.
And apart from their obvious value to metalliferous mineralisation projects, do you think these data will be of value in drawing up regional correlations between geochemistry and health patterns?
Yes, this can already be done on a limited scale, using the atlases to look at individual farms or areas. But if the medical and agricultural data were also in machine-readable form, then it would be possible to find statistically meaningful correlations between the 2 data sets. Then I think we'll be able to make real progress in identifying geochemically related disease.
Well, thank you, Jane. Well, clearly the IGS program's providing lots of very detailed information of considerable environmental and economic importance. Well, we've seen in this program how an understanding of the links between geochemistry and man have been developed. And perhaps we should leave the last word to the first man in Britain to identify the importance of these links.
Personally, I'm quite certain, and always have been, that multi-element geochemical atlases will become a national, indeed a global, cartographic requirement to the benefit of the community as a whole. Just as the first geological map, compiled by William Smith around 1850, is still being updated, so I'm sure these first attempts at geochemical mapping will provide the basis for the future.
And there